So good morning to all of you. In previous lecture we have already discussed the concept of Lagrangian and corresponding generalized momenta, cyclic coordinates and degree of freedom, equation of constants. So in this lecture, what is our objective? Our objective is to simply construct a Lagrangian. In previous lectures we have only discussed the expression of generalized coordinate, degree of freedom, equation of constants for a given Lagrangian expression. But the objective of this lecture, in this lecture I will discuss the concept of Lagrangian for any physical system and how to construct a Lagrangian. Suppose we have any physical system. So in physics we have various physical system like harmonic oscillator, spring pendulum, at-wood machine, particles constructed to move on the circumference of circle, and double pendulum, spring mass system. So there are various systems, physical system. So corresponding to this physical system or these physical systems, how to construct or how to set up a Lagrangian. So the objective of this lecture is to discuss the construction of Lagrangian or how to set up a Lagrangian for a given physical system. So suppose out of these various systems, I will consider the first one is harmonic oscillator, which is spring mass system, the most simplest system and very important system for physics point of view or for any competitive examination point of view is harmonic oscillator or spring mass system. Suppose we have a spring mass system. So this is very famous system, spring mass system, also known as harmonic oscillator. The schematics is and let's say this is x direction and this is y direction. This is the information that we have. And what is our job? Our job is to construct a Lagrangian for a spring mass system. And we know that Lagrangian is basically L, which is function of generalized coordinate, generalized velocity and time explicitly. So, and it is also defined as Lagrangian is kinetic energy minus potential energy. So T minus V. So let us analyze this physical system. So what is this spring mass system or what is harmonic oscillator? Harmonic oscillator is a system which executes a simple harmonic motion. And harmonic oscillator is a system in which our spring mass system is a system which executes simple harmonic motion. In this system, a spring mass system or harmonic oscillator is a system in which a mass m is attached to a massless spring of having a spring constant k. So this is the rest position of spring mass system. If you will stretch this spring, because we want to study the mechanics of this physical system, so or this dynamical system, so let us displace little bit this physical system in this x direction. If you will stretch this mass in this x direction, so this is rest position, and if we will stretch this spring by some force, in this direction, so there is a stretching, and this stretching is, let's say it is x or delta x. So there is a force. If you will apply the force in this direction, so there is a stretching, there is a displacement. It means we are disturbing the equilibrium position of our physical system. So what happened? If we will stretch in this direction, there is a opposite force which try to bring back this system in equilibrium position, and that force is known as restoring force. So restoring force which is minus of kx, and this x is the extension in length under the influence of force, and this is the coordinate system. This direction is x. We can consider it y, z, it's up to us. So we will, in this case, we will consider the stretching is in x direction. So restoring force is F equal to minus of kx. Minus sign means this is opposite to the displacement. That's why we are putting here minus sign. And the restoring force means the force which try to bring back the system to its equilibrium position or initial position. So this is the physics behind this physical system. Now let us analyze the mechanics. So in order to analyze the mechanics, we should know the equation of constants, means mechanical parameters. So we should know at least what is the equation of constants in this system, what is the degree of freedom in this system, what is the potential energy of, because what is our interest? Our interest is to construct or set up a Lagrangian for this physical system. So we should know the expression of potential energy, kinetic energy, then we can only construct a Lagrangian, and once we know the Lagrangian, we can write the Lagrangian equation of motion corresponding to this physical system, and we can analyze each and everything in terms of scalar entity. So this is overall physics behind this physical system. Let us now write the expression of Lagrangian. So Lagrangian for this physical system, so spring mass system is a system or harmonic oscillator. Why it is called harmonic oscillator? Because it executes a simple harmonic motion, and you know what is the meaning of the simple harmonic motion. So Lagrangian corresponding to this physical system of this system is simply L equal to T minus V, where T is kinetic energy and V is potential energy. See, potential energy is a very important parameter in this classical mechanism, because kinetic energy is half mv square or half m qk dot square in terms of generalized coordinate. So this kinetic energy is, so let us write the general expression, then we will see, we will manage our T and V according to the equation of constants. So what is T? T is 1 upon 2 mv square or 1 by 2 m. In Cartesian coordinate we can express our T, which is x dot square plus y dot square plus z dot square. See, and what is our stretching? Since our spring is moving only along x direction, so there is no component of y and z. That is why we are, so in this geometry, from this geometry we can conclude that there is no stretching. The stretching, we apply the force only along this direction. So the stretching, and this direction is x direction. So there is no y and z component. So that is why our kinetic energy is simply 1 by 2 m x dot square. What about potential energy? Potential energy is simply F dot dr. In this case, this is F dx. And what is F? F is a restoring force. So for this physical system, this is the general definition of potential. And if we have an expression of F, then we can easily find out the potential energy expression. So this, in this spring mass system, our F is minus kx, which is restoring force. So this is minus kx dx. So this minus minus will become a plus, and what we have 1 by 2 k x square. So this is the potential energy expression. Now L is simply T minus V. So 1 by 2 m x dot square minus 1 by 2 k x square. Now this is the general expression of Lagrangian. Now we can check check, or we can recognize whether, we can check whether the given Lagrangian is correct or no. In earlier lecture we have already discussed that how to identify or how to check the given expression of Lagrangian is correct or incorrect. So let us see. So how to check? Because in this Lagrangian we can see that there is only one generalized coordinate, that is x, and we can physically visualize this system also, because we are applying the force only along x direction. So the motion is only along the x, the independent motion. In classical mechanics, independent motion or independent way is a very important keyword. If there is a dependency, means there is a constraint, and there is a constraint means there is a limitation, and when there is a constraint, so there is no motion along that direction. So we will only consider the independent motion. So the motion of this mass is only along this x direction. So that is why we can say that there is only, physically we can visualize that this mass is moving only along x direction. So there is only one independent way through which this system can move. There is only one independent way through which this system can move. So generalized coordinate in this system is simply, what is the generalized coordinate? Generalized coordinate in this system is qk, which is x. So there is only one generalized coordinate, and we know that I have already explained the concept of degree of freedom. We can also evaluate the degree of freedom for this physical system. So the number of generalized coordinate is equal to the number of degree of freedom. So number of generalized coordinate is equal to number of degree of freedom. So number of generalized coordinate is 1, which is equal to degree of freedom. So let us evaluate the degree of freedom for this system. Degree of freedom is simply 3n minus k. N is 1 because we have only one mass. So from this physical system our n is 1, that is okay. What about k? K is the number of equation of constraints present in the system. So what is k? This is in plane. Since the motion, this particle, if you write the particle, so what is its coordinate? Its coordinate is simply x, y and z. But the system, this spring mass system is, if you apply the force in this direction, so the motion is only along x direction. So there is no motion along y and z direction. So y equal to 0 and z equal to 0. So this is the equation of constraints. So equation of constraints in this system is simply y equal to 0 and z equal to 0, because motion is along only 1d, along x direction. So k equal to 2. Number of equation of constraints in this system is 1, 2. So there is 2. Value of k is 2. So n is 1 and k is 2. So simply 3n minus 3 into 1 minus 2 is 1. So degree of freedom in this system is 1 and number of generalized coordinate is 1. So we can see that in this given Lagrangian, if number of degree of freedom is equal to number of generalized coordinate, then our given expression of Lagrangian is correct. Otherwise it is not correct. So in this case this is correct, because number of degree of freedom is 1 and number of generalized coordinate corresponding to this Lagrangian is 1. So this is a correct Lagrangian expression. We can also proceed further. So in this way we can analyze, we can construct the expression of Lagrangian. Now we can set up a Lagrangian equation of motion. If you know the Lagrangian, so what is the Lagrangian equation of motion? Lagrangian equation of motion for spring mass system. We know that d by dt of del L upon del qk dot minus del L upon del qk, which is 0, equal to 0 for conservative. Here qk is simply x. So d by dt of del L by del x dot minus del L by del x, which is equal to 0. This implies that what is del L by del x dot? Differentiating this L partially with respect to x dot, so we have mx dot. We have mx dot. And what is del L upon del x? Minus kx. Differentiating this L partially with respect to x, so we have only one x, which is minus half kx square. If you differentiate partially with respect to x, x dot is constant, so this is 0, and we have twice half kx, 2 will cancel out, we have only minus kx, which is equal to 0. So the final profile is simply mx double dot plus kx equal to 0, which further implies that x double dot plus k by m x equal to 0. So this is Lagrangian equation of motion corresponding to spring mass system. This is very famous system in physics. You can analyze classically and quantum mechanically also. So we can express, and even in Newtonian mechanics also, we can set up a differential, we can set up an equation of motion in Newtonian mechanics corresponding to this physical system. But in that case, we need to take care of constant force also, which is irrelevant, which play a no significant role in equation of motion or in trajectory of system or in mechanics of system. So that is why this mechanics is preferred to the Newtonian way. But we will get the same result. Classically, we will get the same result. So this is what? This is x double dot is simply d2x by, what is this? X double dot d2, or in another word, we can write it as, this is simply d2x by dt square plus, let's say this is omega square x equal to 0. This implies that where omega is under root k by m. K is a spring constant and m is the mass, and omega is the natural frequency of your oscillator. So this is again second order. What is this? This differential equation contains lot of information, and this is second order differential equation. And the solution of this differential equation will tell us the actual trajectory of our spring mass system, or actual mechanics of our spring mass system. So what is the solution? So solution of this differential equation, which is d2x by dt square plus omega square x equal to 0. So we can this is second order linear differential equation with linear differential equation, and we know how to deal with the second order linear differential equation with constant coefficient. So using operator method, we can simply find out the solution. So this is simply d square plus omega square x equal to 0. So this is auxiliary equation, d equal to plus minus I omega. We can simply, so using this operator method, we can write the simply differential equation, the solution a sin omega t plus delta r phi. So this is the solution of solution of this differential equation is simply x of t a sin omega t plus delta, and this is the argument. This argument is known as phase, this a is amplitude, and what is this xt? This xt is the simply trajectory of particle. This will tell us the instantaneous position of particle. This xt, this is known as displacement equation, or trajectory of our spring mass system or our dynamical system. And this tells us, if you know, this will tells us that what is the instantaneous position of our system or particle or system of particle at t equal to 0 and at any later time t, at t equal to 0 and at any later time t. So this is displacement equation, and once we know the displacement, we can differentiate with respect to t. We will have velocity, so we can find out the velocity, which is dx by dt. We can find out acceleration, which is dv by dt, or d2x by dt square. We can find momentum, which is p equal to mass times velocity. So these are the mechanical parameter, and this is the objective, and this is known as the mechanics. This is the objective in mechanics, and this is known as the mechanics of this spring mass system, or mechanics of this physical system. So if we have a spring mass system, simple spring mass system, this is known as harmonic oscillator. So corresponding, we can find out lot of information in classical mechanics. We can find out the equation of constraints, which is 2, degree of freedom, which is 1, generalized coordinate, which is 1. So there are so many objective questions that we can formulate with this long answer question. The objective of this long answer question is because it contains lot of objective questions. Someone asks, what is the degree of freedom corresponding to this spring mass system? What is the generalized coordinate? What is the... So let me just conclude. So equation of constraints for a spring mass system, which is also known as harmonic oscillator. Why it is harmonic oscillator? Because it executes a simple harmonic motion. So there are so many questions. Equation of constraints, generalized coordinate, which is what? Which is 1, degree of freedom, which is 1. Third, equation of constraints, number of equation of constraints, number of equation of constraints, which is 2, that is if the motion is stretching is along x. So this is Lagrangian, which is 1 by 2 m x dot square minus k x square. Lagrangian equation of motion, which is mx double dot plus omega square x equal to 0. Position or instantaneous displacement or instantaneous position, you can write it as instantaneous position, which is x of t, which is a sin omega t plus delta. Velocity, we can find out velocity, acceleration, momentum. Velocity, acceleration and momentum. We can also find out the frequency or time period. Time period, which is t equal to 2 pi by omega, or 2 pi by omega is simply k by m. So in this case m by k. So these are the mechanical parameters through which we can find out. So in classical mechanics, once we have a Lagrangian, we can predict each and everything about the system or physical system. So There are so many objective questions that can be asked, or that will ask, or that has been asked in this corresponding to this physical system. This is most simplest system. We have more complex. There are if we have a combination of springs and masses, so in that system we can also analyze the Lagrangian and all these parameters. So corresponding to this small physical system, we have so many questions. What is generalized coordinate? What is degree of freedom? What is equation of constant? What is number of equation of constants? What is Lagrangian? What is Lagrangian equation of motion? Once we have a Lagrangian equation of motion, then what is its solution and what is the physical meaning of this solution? The physical meaning of this Lagrangian equation of motion is simply the trajectory of particle. Means what is the instantaneous position of particle, what is the position of particle at t equal to 0 and at any later time t. Once we know the instantaneous position or displacement, we can easily find out velocity, momentum, acceleration, and what is the time period, what is the frequency. So all are the mechanical. We can evaluate all the mechanical parameter through this classical mechanics. So it's all about spring mass system. Thank you.